Hello, so today we are going to do this problem which is part of Leetcode daily challenge, number of provinces. So what this problem says is we just have n cities and some of them are connected while others are not. And basically a city is connected directly to another city. So let's say city A is connected to B if we have this is connected matrix that we get as in the input, if we have the value for A and B equal to 1. Okay, and that's basically what we call connected directly. And then there is connected indirectly, just if let's say A is connected to B and B is connected to C, then A is also connected to C but indirectly. Okay, that's just the concepts that we have here. And then what we want to return is the total number of provinces. And what do they mean by provinces? Is just a group of cities that are connected. Now it can be either directly, so there is a direct edge, or indirectly where you go through other cities to get to the other one. So it's just a group of connected cities is called a province, and the goal is to return the total number of provinces. Okay, so that's what we are trying to solve for here. Okay, so let's say we have let's say maybe something like this with 3 connected to 4 and 5, and then we have 6. Then in this case, how many we have? We have 3 provinces. Basically, what we are looking for a province is just a set of cities that are connected. These ones are connected, these ones are connected, and these ones are connected. And this concept in graph is just like a connected component. Okay. Now, how do we usually do connected components? You can either use DFS or you could use union find. You could also use BFS if you want. But in our case here, we'll just use DFS. And the way you do DFS to get the connected component is just like, you start from, we know the number of nodes, so let's say n. We'll just go through each node, okay, and see if we haven't visited yet. So we'll keep track of a visited set. If we haven't visited a node yet, then we'll start a traversal from that node, and we'll keep going until we reach all the connected nodes to it. And so, for example, in this case, let's say if we start from 1, we'll just visit 2 and we will be done, and we'll increment our count by 1 because we just started a visit from a non-visited node and went to all the connected ones. And so here we will add 1 and 2 to our visited set, and we'll say we have 1 more. And then we'll go to 2, but we'll find that 2 is already visited, so we skip it. And then we'll go to 3, because remember, we will go from 1 to n. And n in our case here is 6. And so we'll go to 3. 3 is not visited yet, so we'll start traversal from 3. And we'll go to all the nodes connected to 3, so we'll go to 4 and then to 5. And so we'll add those to our visited set. 3, 4, 5. And now we'll increment our count by 1 because we just did a DFS, right? And then we'll go back to our loop. We did only 3, and so we'll check, did we visit 4 yet? Yes, so we'll skip it. Did we visit 5 yet? Yes, so we skip it. And now we go to 6. We haven't visited 6 yet, so we'll start a DFS from 6. And we'll increment our count by 3 because we just started another DFS. And then we'll add 6 to our visited set, but there is nothing connected, and so we stop, and we reach the last n and we stop. Okay, so that's sort of the idea. Basically, we keep a track of a visited set, and we'll try to start a DFS from each node. If the node was already visited, that means it is part of another connected component that we already traversed, and so we just skip it. If not, it means we haven't visited yet, so we start a component from that node. And we'll keep going basically like that until the end. So that's the core idea here. Now let's just code it up and make sure it passes. Okay, so let's code this up quickly here. So what we first want to get the number of nodes, which is so that we can check them. And we have this is connected that tells us whether a node is connected or not. And we are told that this is n by n, so the length is going to be n, which is the number of nodes. And the nodes we have are just the range from 0 to n, okay? In the example I gave, we went from 1 all the way to n plus 1, all the way to n, sorry. But in this case, we can just go from n0 to n minus 1. And that makes the numbering nicer because here we have the connected from I to j. That is easier to do. If you prefer, you could do 1 to n, but then when you are trying to access is connected, you'll just need to do I minus 1. So that works as well. But in this case, we want to keep track also of a visited set, like we mentioned in the overview. And here, if I is not in visited, so we haven't visited it yet, then we want to start a DFS. But we also want to keep track of all the components, and so let's call them components here. And here, because we started from this I, and we visit all the connected nodes from it, this is a connected component, a new connected components. And so we need to increment by 1. And then at the end, we will return the number of connected components. Now we need to write our DFS. So it visits a node I. And when we visit a node, we want to add it to our visited set, and then we want to go through the neighbors. So how do we get neighbors? Well, this is connected, right? So I and j are connected if the is connected I and j is equal to 1. And so how do we get the connected nodes to I here? Well, let's just go through all the nodes and just check which ones give us this, because that's the ones that are connected to I, okay? So this is what's called the adjacency matrix, right? Where the value would be some value if they are connected and another value if they are not connected. There is also, you could, if you choose before starting with DFS, just create your own adjacency list, which basically would be node as the key and then the list of neighbors as the value. So you could do that and do the conversion, but since it's easy to do with just this adjacency matrix, let's just do that. And so we'll just try all of them here, and we'll check if is connected at I and j is equal to 1. That means basically that j is connected. Basically there is an edge I to j, okay, if this is equal to 1. But we also don't want to visit something that we already visited, right? So here we want to make sure that it's not visited, so that we don't keep going in circles. And now, so we go through all of them, we see if they are connected. If they are, then we want to traverse this node j, because we want to cover all the connected ones to I here, okay? And then that's pretty much it, right? So we will mark all the ones that are connected to I and add them to this visited set. So next time we won't start the components from these. We will only start components from nodes that we haven't visited yet. And yeah, that's pretty much it. So this one will go through the connected component, and this one will calculate each connected component separately. So let's run this, let's submit. And this passes, okay? Now in terms of type complexity, usually for DFS it's O of E plus V. So what are the number of edges and the number of nodes? Well, that's just the number of cells is connected, right? So it's at most, so it's going to be O of n squared time. That's what our DFS will do. In aggregates, that's the most our DFS can do, because we never visit a cell twice because of this visited set. So at most we'll do this time. And then in terms of space, we are only using this stack and then this variable. So and we are using also this visited set. So overall it's going to be also event squared, okay? Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.